Hey, grade 8. Welcome to topic 2 of your salt and freshwater systems unit. We are talking today about Earth's frozen water. So, as you found out in the last topic, not much of the water on Earth is actually fresh water, very little of it. And most of the fresh water we do have is actually tied up as frozen water in glaciers. So we're going to talk a little bit more about that frozen water and glaciers today. Frozen water in the form of glaciers, ice fields, and year-round snow and high mountains covers 10% of Earth's land area. So 10% of Earth is covered up by frozen water, ice or snow. And these are natural reservoirs of water on Earth. So they're essentially holding the water. It's not accessible right away without obviously melting it, right? Accessing it, but it's there. In some areas of the world, it is so cold that snow remains on the ground all year. When the snow doesn't melt, it starts to pile up, and as it piles up, it gets more and more pressure on the bottom because more and more weight of snow is on top. You guys probably know snow is heavy, incredibly heavy. I don't know if you remember that snowfall from the winter that was just massive, huge. I ended up shoveling my neighbor's driveway because he's elderly, and I'm like, okay, I'm going to do this. I'm going to be a nice guy. Holy smokes. I was at it for 3-4 hours just trying to get through a driveway and sidewalk because of how heavy it was. Just incredible. And then thankfully after that, my neighbor actually has a bobcat. And so he was kind enough to just start doing every driveway on kind of like my little court there. So then they ended up taking care of my driveway when I was about halfway done, which I was very thankful for because I was exhausted. But snow's heavy. And eventually the weight of the snow compresses the snow at the bottom into ice as time goes on. Okay, so as the weight of the snow presses and presses and presses, you guys know that, snow is essentially ice. It's just not compressed, right? It's not compact. But as it gets pressed and squeezed, then that snow is going to lose all the air in between, and then through little bits of melting and then freezing again, melting, freezing again, you're going to get that ice. Anyways, as pressure even builds up more at the very bottom, we end up having ice starting to melt. The reason why that happens is because ice is less dense than water. So as pressure gets higher and higher and higher, as a result, ice actually starts melting because of the fact that water takes up less space. So when you're compressing something, right, under the pressure, if it can take up less space, it will. So that ice, which is less dense than liquid water, as you learned about in the density units, that ice will start turning into liquid water as that's taking place. And now that there's liquid water, that essentially works as a lubricant in order to allow that ice to start sliding and moving downhill. And that's why glaciers start creeping along by advancing, is because of the fact that at the very bottom of that glacier, you have essentially water underneath of it from that massively high pressure of all the weight of the glacier pushing down on it. This moving mass of ice and snow is called a glacier. Most of the fresh water on Earth is locked up in glaciers, and glaciers directly influence the water cycle by slowing the passage of water through the cycle. It essentially is like a bank, a savings account for water. Once it's in the glacier, it's not evaporating a ton and re-entering the water cycle. It's in there. It's stuck. It's like our savings account, our emergency fund for fresh water. You don't want to access it, right? It's there in case you need it. And it also influences a lot of different things. So for example, you guys know that snow reflects a ton of light and ice. I don't know if you've ever been out in the winter on a really sunny day and you know how your eyes start to hurt, right? Indigenous people used to actually Inuit used to use these little slits on their eyes for snow goggles to let less light in because they were trying to limit the amount of light that was reflecting back from the snow because it actually hurts your eyes over time. all that light that's reflecting back at you. And when it comes to 10% of the earth being covered by the snow and ice, that reflects a lot of the light back from the sun into space. Instead of it absorbing by Earth's surface and heating up the atmosphere and heating up Earth, it instead reflects back. But as more and more ice and snow melts, then as a result, more and more sunlight gets absorbed. So another kind of side thing there. They are excellent storehouses of large amounts of fresh water. They release the water in the summer when it is needed most. I mean, you can imagine that in the summer, that's when we need the most water for things like agriculture, right? Growing crops. So that's glaciers. A glacier that forms on a large area of flat land is called an ice cap. You've heard of the polar ice caps, for example. That is technically a glacier. So when we talk about different kinds of glacier, ice caps are technically a glacier. Ice caps flow outwards from their center. So as more and more snow ends up falling into essentially like the middle and packing in the middle, then it sort of like spreads out further and further and further as it grows, if it is growing. An ice field is an upland area of ice that feeds 2 or more glaciers. So you can kind of think of it as you've got like this kind of field, and then you have glaciers that are flowing down from that field afterwards. So the Columbia ice field covers 325 kilometers squared. It is the largest of all the ice fields in the Rockies, and it feeds 6 major glaciers. So there's 6 kind of like pieces coming off of it that are falling down. Now, I mean, the ice field itself, technically we could call a glacier, but typically when we talk about glaciers, we're talking about these masses of ice that are moving. But all of these are within the umbrella of glaciers. 3 of Canada's largest rivers and 3 oceans are fed by this ice field, the Columbia ice field. So yeah, it's huge. It's massive. If I've never been on a tour, I would really like to, but maybe you've seen like pictures or brochures or the website around this. They have these big, massive tired vehicles that they take out and go around and show you the ice fields. And there was a massive accident actually that recently happened, I think, in the Columbia ice fields. But yeah, it's supposed to be really neat. I'll see if I can find a video. Glaciers that form in mountain ranges are called valley glaciers. So again, we're continuing talking about different kinds of glaciers. Because these glaciers are high in the mountains, the temperature doesn't get warm enough for the snow to melt during the summer, at least not all of it. And these glaciers continue to grow over time and creep along. So when we have glaciers that are high in the mountains, we call those valley glaciers. Another type is continental glaciers, which are huge, very thick masses of ice and snow. These occur mostly at the North and South Poles. So Greenland would be a great example of a continental glacier. Due to all the weight from the layers above it, the ice deep in a glacier is flexible enough to bend, stretch, and flow. And that's again because of the fact that all of that pressure, all of that weight that is pushing down on that bottom layer causes the less dense ice to start turning into more dense water. Water is most dense at 4 degrees Celsius. That's the highest density water can be. So as pressure gets higher and higher and higher, as more and more snow and ice accumulates on the top, that results in the ice below. From all of the pressure pushing down on it, it tries to take up less space by turning into liquid water. And that allows it to flow and move, because essentially you've got almost like a underground river or lake underneath this glacier. I don't want to call it a river or lake because that implies a lot of movement. There is sometimes a lot of movement, but you can kind of think of it as just this large layer of water that's at the bottom of these big glaciers. And as it flows downhill, it shapes itself around the rocks as it flows over it. It spreads out, it gets thinner in wide areas, and it squeezes and deepens in narrow areas. So even though we think of ice as this big, hard rock, it's always moving. These glaciers are bending and flexing and everything, and it's all because of that high pressure and the amazing amount of potential energy that it has up high, and the force of gravity on these huge, huge masses of ice pulling it down, and that force, as well as the high pressure causing things to turn into water and stuff down below, allows it to flex and move and bend as it works its way downhill. When a glacier melts faster than it flows, so we're off of types of glaciers now and how it moves, and now we're getting into kind of why it moves, I should say. Now we're getting into types of movement. When a glacier melts faster than it flows, it looks like it is moving backwards. It is still moving down though. So even when we have a receding or a retreating glacier, okay, retreating is the right word, it is still moving downhill, but it's melting faster than it's moving downhill. So as a result, it looks like it's moving uphill, but it's actually just two things are happening. I'm going to draw a diagram for this. Two things are happening. So here's my glacier, okay? Right here, this is my glacier. It is still moving downhill, but at the same time, it's melting so fast, and it's melting faster than it's moving downhill. So as a result, it looks like it's shrinking or retreating. And that's just because of the high rate of melting. However, if the ice builds up faster than it melts, the glacier lengthens and it's an advancing glacier. So if it's building up still and it's always going downhill, glaciers are always going down to the lowest point. But then it would look like it is advancing, okay, because it's building up and it's moving downhill. Both retreating and advancing glaciers are moving forward and downhill at all times. So you have two rates, or well, really three factors at play here. You have the melting, which is causing it to shrink. You have the growing, which is causing it to advance. I should say advance. I don't like saying shrink here. I'm going to say instead retreat. It's causing it to retreat. Then I have the growing, which is causing it to look like it's advancing. And then finally, I have the going downhill, which is causing it to advance. As long as these two things together is faster than this, the melting, it's going to be an advancing glacier. If the melting is faster than the growing, it's going to be a retreating glacier. But these two factors, these two things are causing it to advance, and this thing is causing retreating. And it all has to do with are these two things happening faster, or is this thing happening faster, the melting? Glaciers give us evidence of the past. This is the neat thing about glaciers. When we take a look at glaciers, we can take a look at the ice cores. It essentially holds a history of what has happened on the Earth in areas where ice is not melting again. It's fascinating. We can even tell the composition of the atmosphere during those times in the ice cores. So what happens is each year ice builds up, and it builds up faster when it's snowing in a season, like we'll call it the winter season. It builds up faster in the winter season and slower in the warmer season. So you can actually see differences. It's like a tree, when you can see years on a tree with the rings. It's like that with the ice, that we have areas that are a little bit different than others in terms of their density and how they look. What's neat is that we can actually figure out from those ice cores different things about the atmosphere and about the Earth. So windblown dust, ash, when there's volcanic eruptions. We're not talking large amounts of ash, but this is all detectable with amazing scientific tools like spectroscopy, right? Where we can see the composition of what's actually in there. Also, gases get trapped in there, so we can actually tell what the composition of the atmosphere was long ago by looking at the composition, the gases trapped in the ice from that time. Radioactivity as well, right? There's radioactive materials that are always around us. Don't let that freak you out because most of it is harmless, but there's always atoms that are decaying with different types of decay. And so we can actually look at that and see what was happening. So a great example, just to talk briefly about this, you probably heard of carbon-14 dating. Normal carbon is called carbon-12. We are all the time taking in carbon-14 and it decays. Okay. As long as we're alive, we're taking in carbon by eating. That's carbon-14 carbon, because some of the carbon we eat, small percentage, is carbon-14 in food and everything else. Well, when we die, we stop taking in carbon-14, but it keeps on decaying in our body, right? So by looking at the amount of carbon-14 in things that we're living, we can tell how long ago it was alive because of the fact that it's changing and decaying into other elements. So by looking at the amount of carbon-14, and this is just one isotope that's tracked, there's many. By looking at the amount of carbon-14, we can actually track then how old something is, how long ago it was alive. I think potassium has a similar kind of thing going on. Calcium, if I remember right. There's many different, so when we date things in science, we don't just use one isotope, we don't just use carbon-14. There's several different isotopes we look at in order to figure out the age. And by looking at all the data together, we can kind of triangulate or specifically say how old it is. I'll link a video about dating things. A dating video. All right, major periods of cooling are called ice ages. There are several factors that can lead to an ice age, that can put the Earth into an ice age. Reduction in the sun's thermal energy, so essentially less sun's energy can make it to Earth. This could happen because of an increase in volcanic activity, which causes large amounts of ash in the atmosphere. So when a huge volcano erupts, like if Yellowstone supervolcano ever erupts, it's going to put us into an ice age, most likely, because of the huge amounts of ash that would be in the atmosphere, which, just like snow, would reflect light and make it so the light cannot reach Earth and warm the Earth. So it'd put us into an ice age. As more and more mountain ranges, if mountain ranges form through tectonic activity, so tectonic plates moving around and got a mountain, then as a result, you could have more and more snow accumulating on that mountain. And again, because of the reflection of light from snow, it can result in an ice age starting because less is absorbed by Earth. Movement of tectonic plates alters the shape of oceans. That can cause it because as ocean currents change, we have these large ocean currents that bring heat, like almost a heat conveyor belt around the Earth. And if those start changing, which actually it looks like they might be starting to change a little bit, which is kind of scary. That doesn't mean that we're going into an ice age, but it's a little bit scary in terms of, because actually the opposite is happening, but it's a little bit scary how things are changing around that. Could cause climate change as well. And then changes to the tilt of Earth is also a factor. If the Earth tilts in such a way that more ice starts accumulating and we get less energy from the sun, then, that can also be a problem. Now, all of this, I don't love how this is laid out because all of this has to do with a reduction in the sun's thermal energy reaching Earth. And these are all reasons why that can happen. So this isn't a point. This is the main reason why ice ages start, is that a reduction of the sun's energy reaching Earth happens for these reasons. So, kind of a little bit of review and a few points with questions. I'm not going to spend as much time on these slides. I know this is already getting to be a large ed puzzle. How does a glacier form? Glaciers are large moving masses of compressed snow and ice. They form when snow piles up and the snow at the top exerts pressure on the snow below. This causes the snow at the bottom to compress into ice, and then as pressure builds up, it compresses even more and turns into water, causing the glacier to move. I'm going to add that to that answer. How much snow must accumulate for glacial formation to happen? 30 centimeters. 30 centimeters, not a ton. It's like a ruler. Okay, that's a ruler length. Once we get 30 centimeters, we can start having what would be called a glacier, because that's enough pressure for the snow to start turning into ice at the bottom. Glacier formation, this is just kind of a neat little diagram. You don't need to know these terms, but just kind of to show you over time how it compresses with pressure and turns into what would be called glacier or glacial ice. How do icebergs form? Icebergs are formed when large chunks of ice break loose from continental glaciers. So like Greenland, for example, right? When you have ice breaking loose from that, that's called calving, which is weird because it's like a cow giving birth, right? Calving. But that's when an iceberg forms, is when ice breaks off of a glacier, large amounts of ice, and then starts floating away, moving away from home to do its thing. Explain the difference between a valley and a continental glacier. Valley glaciers form in mountain ranges. You got some nice pictures there. And continental glaciers are large areas of land like Antarctica and Greenland. And they're different, right? Because what's happening with those continental glaciers is that they're not necessarily creeping along, but they are maybe growing as more and more ice compacts on it, and then it spreads out. I almost imagine it like a really loopy liquid when you pour it onto a table and that starts like spreading out. I kind of think of it almost like that in my mind. These ice cap type glaciers or continental glaciers. They're different, but similar in how they work. What conditions are necessary for a glacier to advance or to retreat? So the flexibility allows the ice to flow away from areas of accumulation and advance. If ice melts from a glacier faster than it is replaced by new ice glacier, and it advances due to movement, right, the slipping at the bottom and so on, then it retreats. That's it. That's glaciers. Yay, frozen water. Okay, so what did you get out of this, hopefully? Hopefully you understand a little bit of what a glacier is. It's just essentially snow that's compacted into ice. You understand some different types of glaciers. So you know about ice caps, continental glaciers, you know about valley glaciers, and you know about ice fields. Okay, you know that stuff. You know why glaciers move, the turning of water down below, and that causes it to kind of slip and slide around. It's always moving downhill. You understand what causes a retreating versus an advancing glacier, and it has to do with the rate of melting, the rate of growing, and then how fast it's moving downhill. You understand how an iceberg forms. Trying to think. That's pretty much it. And you understand, of course, that about a large amount, 2/3 of our fresh water is tied up in glaciers, and it covers about 10% of Earth is covered by ice and snow. All right, that's it for today. Have a good rest of your day.